So chapter 7 started with Newton's method, which you also have Newton's program in your calculator. Okay, we're going to now, which we also did in AB. Now we're adding Euler's method, which is getting us closer to the end of chapter 7. So I want to go back and just think about Newton's method for a minute. Remember, this all predates calculators, right? These guys were working without the luxury of having a calculator. Newton's method took a curve, f of x. He picked a point on the curve, say point A, created a linearization, which is the same thing as a tangent line, at point A. And Newton's argument was okay. Newton's argument is basically my line is just as good as the curve for a small little section. Okay? But eventually the gap between the two will become significant and my line is no longer accurate anymore. Okay? So Newton was going with it's good enough for a small area. He called it delta small. Okay? That's where we get the D in differentials. Okay? So Newton's argument was Newton's position. His L of x was just as good as f of x. Okay, that wavy means he's not saying they're equal. He's saying they're approximately equal for a small interval. And last year, we had to talk about, well, will it underestimate or will it overestimate? Right? Okay, and he would acknowledge it's going to be close enough for a small interval, but I know that it will underestimate if the concavity is positive, and it will overestimate if the concavity is negative. Okay, but L of x will exceed f of x as an overestimate if the second derivative is less than 0. And L of x will be an underestimate if the concavity is positive. So that was Newton's position, and he just calculated a tangent line. So Euler, remember Newton's in England, Euler's German. Euler's probably friends with Leibniz. Okay. So Euler decides to improve upon this method, says I can do better. All right, so here is Euler's method. I don't know. I'd have to look up his birth year. They were contemporaries? I'm not sure. I'd have to look up. Yeah, I'd have to look up the birth year off the top of my head. Oh, I don't have Siri turned on. Okay. So Euler said, all right, I can do better. I'm going to take the same f of x, and I'll start with the same a. And I'll start even with the same tangent line. Now you have to imagine that we're zoomed way in here. When the gap became significant, Okay, so when you notice that the gap becomes, gap is, I'm not comfortable, that gap is getting too much. Euler said, well, why do we have to stay on a straight linear line like that? Why not, when the gap gets significant, why don't we stop and recalculate the slope and turn our line so that it's following the turn of the curve? And when that gap becomes significant, we'll pick another point and we'll recalculate the curve and we'll do it again so that we stay close along the curve the whole time. Okay, don't just stay on Newton's line and just blindly follow Newton's line off to, infinity and beyond on that slope. Why not adjust, make little teeny adjustments as we go, and then we could stay close to the curve. That's his basic method. So it takes multiple computations. All right, so we're going to practice that by hand, those computations, and then the calculator allows you to do a whole bunch of those computations really fast. It's like we computed RAM with small amounts of information, and then we let the calculator do RAM for us with 50 rectangles or whatever. Okay, so that's the basic idea. Okay, so here's how it works. All right, start on a curve. Sorry. At 2, 0. With a slope dy dx equals x plus y. Estimate f of 3 using Euler's method with 5 intervals. So we just got to keep track, and I've kind of created sort of a table for you to help you keep track as we move. All right, here's my first point. I'll calculate my slope, and then we'll get to the next point, and we're going to turn and calculate a new slope. And so I kind of have a way for us to, I hope, keep track of all of this. So start with x and y. We're going to add to it, but we know that the first x and y we're starting at is 2, 0. If we're moving with our goal of getting to 3, x equals 3, but we're doing it in increments that are 5 subintervals, how long is each subinterval? 0.2, right? So we will be moving to 2.2, and then we'll move to 2.4, and then we'll move to 2.6, and then to 2.8, and then we'll ultimately stop at 3. We will be finding the y value as we move along, and then each time we get to a new position, we'll recompute the slope. So the slope is not going to stay the same the entire time. But let's figure out what our slope is for starters. So our slope for starters is the derivative x plus y. Well, we've got x and we've got y, so what's our slope going to be? 2. We want to take the delta x, which is how far we're going to move, which is going to be 0.2. We want to multiply it by dy dx, which is the slope itself. And look at the math there. If you take dx and multiply it by dy dx, what do you get? Dy, which is dy represents how much your y is going to change. So we know our x is going to change by 0.2. We know our current slope is currently 2. So 2 times 0.2 is 0.4, which means our y should change by 0.4. So what is our new next y value? 0.4. Because we just went from 0 to 0.4 as a change. So that's the new position, that's the new point. Yeah? I took 2, 0, and I plugged it into x plus y. Good question. I did that. I kind of skipped over that. Okay, so now we're going to find the new slope. So we've moved to a new position, but we're going to make a turn. And so we'll take this new current x and y, and we'll plug it into x plus y. What do we get? 2.6. That's our new slope. All right, then let me erase a couple things here. Okay. Our increment is still 0.2 because we're going to move another 0.2 in the x direction. Our slope has now changed to 2.6. So 0.2 times 2.6 is 0.52. That's how much our y should change. So what will our new y be? Point how much? 0.92. We're adding it to what we had before. We're changing it by that much. Take the 0.4 that you used to have, and you add 0.52. Then we calculate our next new slope. So we take now the new position, our next point, we add x and y together, we get 3.32. If our new slope is 3.32, our y should change by 0.2 times 3.32, which I've already worked out for us is 0.664. So what's our new y now? Yeah, 0.92 times 0.664, which is 1.584.
Times or add?
We added them. Here, Justine, let me, okay.
No,
So,
no, I
oh, you got it? Oh, okay, yeah, okay. We're multiplying on the far column, but then we're adding, in the x and y column, it's always adding.
Yeah.
Add 0.2, add 0.2, add 0.2. In the x column, we're adding consistently.
Yeah.
In the y column, we're adding something different. All right, the next one, 4.184. So 0.2 times 4.184, that's 0.8368. So you add that to the y, you get 2.4208. Plug that into the slope, 5.2208. Bless you. Multiply 0.2 times 5. We're almost done. 08. We get 1.04416. Add that, and you get 3.46496, and you stop. And that is Euler's method of estimating what f of 3 was. And he was more accurate than Newton to the, like, 10,000th of the decimal place. Okay, his method significantly improved on Newton's method.